our education. We met last year or last May. And we promised we're going to have research symposium a year. So today we have assembled a program from not only the faculty from OSU but also two industry. Before that, maybe share some updates about our ICDT. Some notable happenings. First, we partnered with Idaho National Lab in their university National University Consortium program, and this program will expand our portfolio in cybersecurity research and also present financial support. In last month, we also had a visit from ASF for the scholarship service program, and we also got the support from our dean, and very likely we will have space for the students, which are undergraduate students, they can meet, and also potential office space for our ICDT. And so we also got interest from the 179 cyberspace wing in Mansfield. In July, we will host the Ohio Cyber Guardian exercise. So you can see, right? We have, in the past few months, we do have some achievement there. Speaking of the research dollars, the metrics to pay the faculty. So we received various fundings from like ASF, ASA, and DARPA. By the way, for faculties, please, when you submit proposal, you have to list the ICDT, such that we can know, we know you submit proposal. In terms of education, right, the ICDT has three pillars: research, education, and partnership. I just talk about research, then for education, past several months, right? This is show you the metrics we obtained various fundings to support our education program. For example, the Crew to Grade, this is from the university, and they support us to develop the new capstone course for computer science and law. Last year we received the advisory. We were part of the advisory program. So that is from the DoD and some state funding as well. Okay, as I mentioned, today is a research symposium. So what's the research landscape at Ohio State or ICDT? So here I organized our research into different buckets, from foundations like cryptography theory and algorithm, and to the techniques like AI and machine learning or system software and so on, and domains such as agriculture, manufacturing. So at Ohio State, big university, so we cover various sectors. The ones I has highlighted, for example, manufacturing, energy, transportation, communication, those are the ones we will have talks today to cover those. And also includes like AI, machine learning, system and even this information. So yeah, this is the program. And as I mentioned, we have two keynotes for industry. One in the morning, the other in the afternoon, and after that will be the talks from the faculty, and last one is a panel to cover the recent developments in the language models and security safety. So how many students? How many attendees? So well, we have as of yesterday, we 55 registered attendees, 16 from faculty, 16 faculty and staff, and also 5 from off campus and more than half of them, half of them are graduate students, more than half of them are students, and 7 undergraduate, 27 graduate students. So you can see like we faculty and staff from various departments, such as CDME, of course, most of them from computer science and engineering, myself. So you can see where are those these. So next, maybe let me introduce today's keynote. So Aaron Miller is going to talk about security in the future. Or cryptography. So the slides. So let me briefly introduce Aaron. Aaron right now works in Daiwa, and he's the strategic leader in Daiwa, and so we pull the bio. Strategy leader supporting the domains of secure systems. And he has co-founded 2 startups providing tooling and the capabilities that leverage formal methods to help create trustworthy systems. At Daiwa, he works with leading researchers across the world to identify, advance, and transition the best technologies to improve the way we build software and cyber physics systems. Aaron's expertise enables him to work with researchers, end users, organizational leaders to identify paths for adoption of emerging technologies that have transformational impacts. Aaron earned his master's degree in system engineering from the University of Dayton.
Great. Thanks, CQ. Yeah. Appreciate it. Thanks for Ohio State for holding this today. It's always good to get onto campuses and be able to kind of connect in the R&D world back into industry and all that type of stuff. So I'm from Daiwa. There's also another logo up here, Naomi Microsystems. It is our spin out that is focused on cryptography and silicon design. And so we're going to talk a little bit about kind of our viewpoints on cryptography and kind of where things are going. So, just to start from the basics to make sure we're all kind of on the same page, information security is really where we get into the aspects of cryptography. Some people say there's 3, some people say 4, we say 5 aspects of what information security and cryptography really mean. But we're really looking at the aspect of confidentiality, integrity, availability, authenticity, and non-repudiation, which basically gets to the point that who is sending you the data, that the data is correct, that the data is protected, and that nobody can get access to it. And then when you are sending it to somebody, you're sending it to the person you intend to send it to, right? And so we've been using cryptography since Caesar created something called the Caesar cipher, creatively named, a very long time ago. And it's always been this realm of trying to make sure we protect the data and the information that we own. So we've been obviously you don't need to look very far into the headlines, and unless you have your head completely in the sand, there's all types of risks that are coming out in the world of cybersecurity right now, and a lot of them have to do with the aspect of data thefts and those types of things. And so we'll talk a little bit about why that's happening today, and why it's preventable, and the fact that it's really not a matter of basic science that needs to be invested into. It's other things that we need to be able to look at. And so whether it's people taking malicious acts like insider threats of sharing data, or whether it is aspects of being hacked or and having your data basically held ransom. There's aspects that our data becomes available in public aspects that enable people to take advantage of that. And it's everybody's data, our data, that becomes very valuable, whether it's our personal data, intellectual property data, customer data, financial transactions, healthcare data, et cetera, et cetera. So what we need to be able to move forward here, turns out that, from industry, if there are people that are in industry here, what we want is to be able to, we need use cases, right? That we can apply new aspects of cryptography methods to that enable us to create the scalable implementations that enable us to protect our data against the emerging threats. From researchers, we need to advance the math of cryptography to the point where it becomes usable for the use cases, right? So ZQ had the things up there at the bottom was theory, cryptography was down there at the bottom. What we have to do from a research perspective is traverse his chart to get all the way to the top where the industry is. And candidly, right now, guys, in the computer science world, we suck at that, right? We're really bad at it, right? And it's not as a society. We need to get a lot better at it, right? And so, like, if I ask you to take one thing away from a researcher perspective today, is like invest time in understanding where you need to meet industry, because you can create the greatest theory known to mankind, but it's useless unless somebody is willing to pull through that thread. At the same time, industry needs to meet and come down and provide the use cases for where researchers need to be able to thrive. If you're students, right, you're going to be taught aspects in the aspects of cryptography that there's common ways that if you're a computer science researcher, you're going to be taught to say, hey, never go bake your own crypto. Use somebody else's crypto module. Well, the problem is if we're doing that, no one's building new crypto modules for people to use, right? And so we're going to talk about the fact that here that there's different ways to go about looking at this stuff. And right now we have this really, really interesting chasm that we've created, and when we look at data at rest, data in transit, and then data while we are in compute, right? So we have really solved a problem in the sense that data at rest, we can protect that. Right? You can steal that data, but it's going to be encrypted. Without the keys and stuff, you cannot encrypt it. It's not very useful. When the data is in transit, for the most part, we've solved that as well, right? We can protect the data as we have it going in transition. Problem is when the data is being computed, right? We process our data in the full and open. And that's where we have our risks, right? So another viewpoint of this is I have data and organization A is processing on that data. We encrypt the data, we pass the data to organization B, and then the person on that side unencrypts the data from what we send them, and then they compute on that information on their side, unencrypted, right? These types of processes at a very fundamental level exist across pretty much every industry known to mankind. And we basically treat these things and an issue that creates sneak attacks, right? When that data is unencrypted, we have risk that exists in those two endpoints. What we need to be able to do is understand that there is not a one-size-fits-all premise for the way that we need to be using cryptography. When we're dealing with cryptography, we fall back on the laurels of the algorithms that already exist that were predominantly written in AES 256 or SHA 256. And we all go out and we find those algorithms. We use the same one over and over and over again to try to protect our data. But it requires us to go through the process of unencrypting the data in order to compute on it. It turns out that math is good and cryptography is nothing more than really complex math that cryptographers have solved for, right? So looking at this a little bit differently, right? We have data that's collected, we have data that's stored, it's all encrypted except for one piece here on the end, right? It's decrypted. And so we decrypt these things in our data centers and on our servers and those types of things. So as we look at this, right, we have, like I said, we solved the math. We don't need to invent new math. What we need to invent are methods of implementing cryptography across use cases or in specific areas. I was talking to Carter here earlier today. We have this notion in the sense that we're going to create one software algorithm in general purpose use. Do we have one manufacturing line to produce all physical goods known to mankind in the United States? No, we don't. In fact, if I'm going to build a single automobile, I have thousands of assembly lines that contribute to the manufacturing of that single automobile. But yet, for some reason or another, when we start putting things into software, we want to treat software as if it's a general purpose solution. that's going to be implemented on everything, no matter what the use case is. And in cryptography, we have lots of other tools to use other than AES 256 and SHA 256. We've got the math done. We've got algorithms written, and there are things that are out there in the realm of zero knowledge proofs, private set intersection, private set membership, multi-party computation, and homomorphic encryption. We choose not to use them. We choose in industry not to make investments to advance these capabilities. We choose in research not to be able to advance the research to the point where we can create capabilities and methodologies. We choose not to teach things and communicate things in the classes for which we teach. I gave Carter, we were talking earlier, I gave him props in the sense that he said he at least mentioned ZKPs, zero knowledge proofs, in his class. That's fantastic. But when we teach cryptography, we need to teach the notion, and when we're talking about cryptography, whether it's a systems engineering class, a computer science class, or whatever, we need to teach the premise that there are other mathematical algorithms and other cryptographic solutions that exist, like ZKPs, PSIs, PSMs, MPCs, and homomorphic encryption. So if we want to solve for these problems, and I'm going to dig into one detail, one of these, I'm going to dig into homomorphic encryption. What we need to be able to do is to figure out how we can eliminate our risk, which is where we are doing data and compute. So in the FHE realm, this is fully homomorphic encryption, we can eliminate entire classes of risk because we keep the data fully encrypted. So again, going back, we decrypted here on the right. And then in fully homomorphic encryption, we use encryption to actually enable the processing of data while the data is fully encrypted. So the data never becomes unencrypted. Right? A lot of people would say that that's black witchcraft. And they don't believe that that's possible, and they don't trust it. And those are excuses for people not to adopt new technology, right? So what we want to be able to do is, if I use an example here, the simple example here is show me a list of container ships leaving Shenzhen on April 1st. Okay, the sensitive information here is Shenzhen and April 1st. I don't want to have that information. If I'm a logistics person, I don't want to communicate to other people that this is how I want to ship information, my goods, right? A more complex example is find me the cheapest transportation plan to ship a container that weighs 2,492 kilograms from Shenzhen to London starting on April 1st, but it must arrive in under 3 weeks, right? So there's lots of personal and sensitive information here. And what we can do is we can then take out all of this sensitive information that we don't want to share, whether it's intellectual property, whether it's personally identifiable information, whether it is financial information, bank accounts, healthcare information, or whatever, logistics information or competitively sensitive information. We don't want to turn that over. And so we can then obfuscate this information utilizing full homomorphic encryption. And so the way that like I said, the way that fully homomorphic encryption works is that it's a software package that enables the parties to be able to make data available to another party, and then have that party then ask questions of that data and then get an answer. The party that's asking the question, their data never becomes unencrypted. So all of this red information, when they're asking the party that has the data to answer the question, it never gets exposed. At the same time, the party that is answering the question never exposes their data either. It's all done through software algorithms that are created that enable you to have these interactions. So the challenge that we have is that right now it's 10,000 times slower to process fully homomorphic encryption than it has been in the past. And so industry chooses not to use it. That's a pretty good reason. However, we can then invest into research to do hardware software co-design that enables us then to speed the computational efficiency of the hardware software co-design piece so that we can then generate a more productive solution. So in Niobium Microsystems, we have generated and model what is the fastest fully homomorphic encryption chip in the world. Now we are going to be getting that chip back in May, next month. And we're going to have a lot of very nervous engineers sitting in a room watching a very tiny piece of silicon to determine whether it actually works or not. But if it works, we then are in the room to be able to go do use cases in industry, right? When we look at these other types of cryptography that sit out there, we're in a situation where we have to make the same types of investment to advance those cryptographic implementations in the exact same way. And we need to understand what the limitations are from industry. We need to be able to understand how we need to move those types of things forward. So when we look at the aspect of fully homomorphic encryption, we look at other examples that sit out there. We have some other aspects such as, can we keep, in general, can we keep things, private? But like, we could look at cloud computing. I can make an entire infrastructure on the cloud computing side completely encrypted and never unencrypted, but give people the ability to ask thousands, if not millions, of questions to it on a daily basis. And the data is never unencrypted. It's never at risk. If I wanted to be able to look at fraud detection, and I wanted to be able to give analysts the ability to identify fraud, whether it is financial fraud, healthcare fraud, academic fraud, or whatever, we can then make available gigantic pools of data that typically are not made available because of its sensitivity with privacy data, personally identifiable information, intellectual property, banking account information, and those types of things. We can make these pools of data available to large masses that then enable us to be way more efficient at utilizing other types of algorithms to identify where fraud is existing in our infrastructure, in our systems. If we wanted to be able to create better efficiency in sharing of healthcare information, we can utilize fully homomorphic encryption to more efficiently process insurance claims, share data files between physicians or doctors' offices or the physical therapists and the such. We can even then find ways to be able to share information with family members or others that would be necessary to have that type of information. Again, without ever making the healthcare data available to anybody in the public domain. And then lastly, if we wanted to be able to share the insights that we have through very large organizations that have gigantic volumes of data, we can, again, keep all of this data private, make it fully available, and then, be able to enable that power of that data to be made available through, questions that we ask, right? So these are all various use cases that give us the ability to really change the way that we process data. Because in every single one of these situations right now that I just walked through, we're utilizing SHA 256 or AES 256 in some way, shape, or form, which then it creates opportunities for risk on both ends of the equation. And if we start to implement and adopt these new forms of cryptography, we can completely change the way that we protect our data, eliminate classes of risk. But again, it all starts with our ability to move the research forward and where we have been at in the academic institutions and organizations like Galwa and others in Patel that are trying to tackle this type of work. So I think I've got a little bit of time that I guess I could take any questions or something like that. If there's any questions. I got a couple other here, right? This goes into AI models. We can utilize these private data sets to be able to help train AI models in new ways. I know Jeremy will, talk about some of those types of things later, but how can we utilize encrypted data to help train models that we can create without ever putting that data at risk as well. That's another use case that sits out there as well. So with that, I don't know if there's any questions or anything on that basis. Yeah.
I guess the question is, aren't we somewhat of a victim of our own? How do you determine success? But the fact that we have something that works, a lot of people fall back on the if it ain't broke, don't fix it. And so that tends to breed complacency.
Yep.
So again, I'm kind of going the line of how do we break through those barriers?
Well,
because otherwise nothing's going to change.
Yeah, I don't know if there's any human factors researchers in here. I know that Julian and ZQ are trying to get to like cross domain research concepts. But no, I agree with you, right? I think that like a lot of systems engineers or a lot of the people that own the networks or the data structures, they have this notion that, well, I can't use something new because it's risky, right? Nobody's ever gotten fired for doing something that their boss did before them, right? And so, the challenge is very clearly, it's not working right now.
Agreed.
Right. And so the sooner that we just become honest with ourselves in the sense that like our data is pretty well unprotected anytime we're processing it right now. The sooner that we can start to actually have impactful change. I think the other challenge is that some of these technologies are definitely not ready yet. Principally because there hasn't been a lot of demand to change. Right? If we had more demand to change, we could, get to the end result a lot faster. I mean, even for us with the FHE use cases, it's really, really hard for us to find people that want to be able to take that leap. And because when I say you're going to process on data fully unencrypted, there's a level of trust of people seeing the data, touching the data, and having access to the data, and being able to know and prove that the question that they answer really is in the data, right? And so the leap to be able to just process on something and you literally are asking a black box and then getting the answer back, it's tough. But it's I think we need to find the right use cases and figure out how to move forward. But right now, it is as much a people problem right now as it is a computer science problem. Yeah.
Did I understand? So basically, you're about to release a chip or test a chip that is going to speed up homomorphic encryption.
Yes, sir.
And then after that, is you looking kind of in a peripheral fashion, or is it baking it into industry standard motherboards, et cetera, both?
Well, we're going to be packaging in May, and then we'll be putting it on boards and servers in June.
Okay.
And the goal is that we are testing it and utilizing industry relevant and specific use cases by the end of the summer.
Oh, that's awesome.
Yeah. So, we've got room, to be able to really play in specific use cases. Great news is that people are, we'll pay for it. If an industry partner wants to go do a use case, we'll pay for it. We just really need use cases.
I think multi-layer security environments is an awesome place to use that type of encryption. But to your point, it takes so much compute right now to do it that it's ineffective. But if you've got that, we should talk.
We do.
Thanks.
On model, we've been proven out to be we'll be the fastest in the world on encryption. Well, our pickups are going to be somewhere around, it looks like, 3,700 times faster than current.
Oh, wow.
Yeah. So
Are you local?
we have an office. So Niobe has an office and headquartered in Dayton. We have a larger office here in Columbus.
Okay.
Yep.
So we do have time for questions.
How do you compare homomorphic encryption with other solutions and trusted execution environment for software-based approach?
Yeah, just like software-based approaches.
Or trusted execution environment, the hardware and the software-based approach?
Well, so it's all software, right? But the challenge, what it is it's different implementations of mathematics that we're really trying to get towards, right? So if so you have to choose a cryptographic method or set of algorithms or implementation structure, and then once you choose that, you're going to implement it in the software. So all of these trusted compute environments are traditionally using the AES AES or SHA 256 mechanisms of cryptography, which are create some challenges for us because at some point in time that data becomes unencrypted. And our data is now at risk, right? And so what we want to be able to do is to start to implement these different types of mathematics, right? To advance the implementations and create higher levels of protection. So each cryptography concept, i.e. private set intersection, multi-party computation, AES 256, fully homomorphic encryption, is a separate mathematical cryptographic structure. And then how we process that is created in software that then requires us to use a certain amount of compute. Right. The reason that fully homomorphic encryption is so difficult is because the computation of the mathematics fully homomorphic encryption is crazy complex, like super crazy complex. I mean, and so in order to create the efficiencies, that's where we have to do specially designed hardware in order to have the efficiencies to do that computational, to create that computational efficiency. In traditional cryptographic implementations, we just try to layer on these additional software pieces, which I think is what you're getting at. And we're trying to add different protections, but at the core of it, the cryptography is still the same. It's not changing.
Two points or two questions. First one, sounds like you're in essence making a graphics card just for FHE.
Yeah, sure.
From a simplistic standpoint.
Yeah.
Oh, thank you. And then second point, more of a question. And again, I've read about FHE, but not in the implementation standpoint. I keep hearing all the buzz about quantum safe, and that's going to go down that road. Does this offer assurances in this space? This plan, I understand now, especially, is gather all the data you can. We'll crack it later when the quantum is stable.
Yeah. So AES 256 and SHA 256 is not quantum secure, right? And so there are new cryptographic implementations that are going to replace those, but they would still require you to unencrypt the data on the compute side, right? And so these other mechanisms, such as like multi-party computation, fully homomorphic encryption, are categorized as quantum proof or quantum resistant at a minimum, right? So yeah, it does address the quantum piece. Going back to your card piece, we are very much like NVIDIA, right? NVIDIA created these AI processing chips that are more efficient at processing and training models, right? Like you wouldn't want to use the chip that we're building to try to train an AI model. We would suck at that, right? Again, going back to the notion of don't just use general purpose things, create specific implementations of things. And so we can create that efficiency by doing that. So the greatest news in the world is actually that NVIDIA just released their price point of their new chip, and it's going to be somewhere between $30,000 and $50,000 per chip, which is fantastic because now that makes attainable things like fully homomorphic encryption, where we need to put in a server because the servers are going to run. I mean, they're not going to be cheap, right? And so it makes the price point of attaining this completely relevant now when we're looking at the compute structures of where things are going. Anything else?
So maybe I have a question. You showed a great use case of query.
Yeah.
To do the query of your homomorphic encryption. What other use cases? So smart.
So fully homomorphic encryption is very much going to be centered around the query use case for the foreseeable future, right? I think that the AI training model concept is kind of the next one to be tackled, but it's probably a little bit further off. But really right now, being able to utilize fully homomorphic encryption to automate, for example, like health insurance claims processing, right? Where basically you have one system query another system, get information to do what they need to do on the other system, right? That's going to be the bread and butter for fully homomorphic encryption. It's very much going to be in that processing realm.
More questions? As Ara, you'll be here today, right?
Yeah, I'm going to hang around here for at least through midday. I do have some meetings this afternoon because work continues to get in the way.
So please feel free to reach in if you have more questions. Next, let's go to our faculty talk. It's going to cyber systems. From Carter is our assistant professor of the computer science and engineering, and he joined the OSU 2 years ago from Georgia Tech. His research interests are cyber-based system security.
All right. Hi, good morning. Thanks for coming. As EQ said, my name is Carter. I'm an assistant professor here at Ohio State in computer science and engineering. And in the 30 minutes that I have, I'm going to talk a little bit about cyber physical systems. So first of all, just setting some basic groundwork, making sure we're all on the same page of what is a cyber physical system. So this is a term that has become relatively trendy in the past couple of years, especially in areas like the Department of Defense. And it's a sort of catch-all term for any device where you have a cyber component. So something that performs computation and then a physical component, something that takes in information about the world and then manipulates that physical world in some way. So a lot of terms that you're familiar with fall under this umbrella of cyber physical system. Your autonomous vehicles, your conventional human operated vehicles, if they have some kind of microcontroller or something of that nature, industrial control systems, SCADA systems, these all fall under this umbrella of cyber physical. So what makes cyber physical so special and why it's been getting so much attention in recent years is that reasoning about the security of a cyber physical system is very different from reasoning about the security of a traditional IT user program. Something that we've been doing for a lot longer and that we're much more comfortable with tackling. So for example, for those of you who do vulnerability research, you're probably familiar with types of vulnerabilities under what we refer to as memory safety. On the theory side, we break memory safety into spatial and temporal memory safety. And then from there, we get classes like stack overflow, heap overflow, format string vulnerabilities, use after free, double free. These are all kinds of vulnerabilities that lead to memory corruptions. And these are vulnerabilities that we've been tackling for enough decades that we have a fairly strong understanding of what these are, what they aren't, how to model them, and so forth. When you look at a cyber physical system, those familiar, comfortable classes of vulnerabilities typically don't apply in this environment. These are, as opposed to traditional IT systems, more on the flavor of real time. They're designed to be much more reliable and consistent. So a lot of times they avoid or outright don't use dynamic memory management. They avoid the use of variable sized buffers. And basically a lot of the building blocks that would lead to a memory safety vulnerability just aren't there. So if you try to approach cyber physical systems like you would a traditional IT program, you're going to find very little, if anything. And then the other thing is the connections. So in an IT system, we like to think that if something comes from the outside, it's untrusted. If it's from the inside, it's trusted. And the most obvious way we like to think about that is it connected to the internet? Yes, no. In a cyber physical system, what exactly are the ingress and egress points are a little less obvious. Think of like a drone, for example. A drone might only have point-to-point communication with a ground station. So how exactly do you model that and what constitutes an exploitable vulnerability as opposed to just kind of a interesting factoid, but not really practical? So as security analysts, when we're trying to analyze these cyber physical systems and find exploits, and specifically, I'm going to take the perspective of a reverse engineer. So I have a piece of hardware. I have this cyber physical system. I might not have full information about it because I'm not the manufacturer of it, but I want to somehow assure myself that this is going to behave how I expect it to behave. So as a reverse engineer, I'm trying to understand what does this system do? What does it interact with? What are its capabilities? And ultimately, is it vulnerable? Or is it, for example, backdoored? Maybe there's an extra feature that wasn't supposed to be there, but someone slipped in during the manufacturing process. And this has become particularly tangible in recent years because cyber physical systems are popping up all over the place and even in ways that we don't expect. So this comes from an IEEE article that was published a few months ago. These photos were taken in Ukraine. And as you can see, this is not a multi-million-dollar military weapons platform. Yes, they actually use for certain types of missions, certain tasks, commercial off-the-shelf drones. In this case, a DJI drone that they 3D printed a mount for and essentially attach some small explosives to. So we're seeing cyber physical systems pop up in all sorts of places and pop up with more frequency and greater scale than we've seen in the past. So as a reverse engineer and a security analyst trying to make sense of a cyber physical system, in the perfect world, what I wish I had was the ability to pull the code and data off of that system and run it somewhere else, somewhere simulated or emulated, where now I can add all the instrumentation that I want to see what it does. I can simulate all these different environments, all these different scenarios without having to physically construct them, and not be constrained by the limitations of the physical deployed hardware, the limited debug interfaces and stuff like that. Unfortunately for Patrick, though, rehosting, while it is an attractive capability, it gets a little more complicated when you try to go out and do it. You don't have to worry about this flow chart, but what this does is it covers every possible step you could employ in the process of attempting to achieve a rehost, taking the code from a physical system and running it in a simulation. And I think the best way to get across the challenges with this rehosting process is with a story. So keeping in the back of your mind this flow chart and these questions on the right here in mind, what I want to do for the remainder of my time is I want to talk about a actual use case. So a little less than a year ago, DARPA announced this program called FIRE. It was a program for streamlining and improving the efficiency of reverse engineering cyber physical systems. As you can imagine, my lab, Battelle, others were very interested in this program. And as part of preparing a proposal for this, I wanted to do a proof of concept, basically try this out and get some firsthand experience of what it's like to try to reverse engineer a cyber physical system. So shout outs to my student Bayen in the back who helped me on this 2-day sprint. And in the course of basically 48 hours, we wanted to take a DJI Phantom 3 and find the smallest, simplest, but realistically viable exploit that we could and just see what happens. So once again, pay attention to the work that we had to do and think about in the back of your head, what could be done differently from a methodology standpoint to do this faster, better, and larger scale. So one of the reasons why we picked the Phantom 3 for our topic or our target is that, as you can imagine, given only 48 hours, we did not have time to go out and buy a cyber physical system. And what's nice about DJI's drones is that enough people are interested with tinkering with them. There's actually already high resolution photos of all the hardware components for most DJI drones floating out there on the internet. And even some function level diagrams from hardware teardowns. So as it turns out, one of the first things that's interesting about Phantom 3 when you rip it apart is that as compared to a traditional computer where it's a very centralized system, you have a CPU, you have a motherboard, and then everything kind of fans off of that. In the case of the Phantom 3, it's a very decentralized system. To use an analogy, if your traditional computer is a dog or a mammal, the Phantom 3 is much more like an octopus. And if you don't understand that analogy, look up how the nervous system of an octopus works later and prepare to be very confused because it's very different from how a mammal is designed. So we have these high resolution photos. It turns out the Phantom 3 is actually about a dozen or so boards all connected together with cables, and they all have their own processors and their own degree of autonomy. So we have our photos, playing the surrogate of a physical hardware teardown. The next question is, where do we get the code and data? Sometimes this is a very difficult process. And the case of this case study, we were able to, I guess, cheat a little bit, which is that DJI actually releases some of their firmware on their website for patching and updating purposes. So we wrote a web scraper. We ripped every single firmware off of their website. Don't tell them that. And it turns out some of the firmware we pulled were for the Phantom 3. So, okay, great. We got our firmware downloaded, this P3X bin. And then the next challenge that we ran into was actually getting that into a usable state for program analysis. As it turns out, because the Phantom 3 has multiple processors on it, and each of those need a program to run, what DJI releases is essentially a glorified zip file, or at least that's what we ultimately discovered. So what they do is they take each of the firmware for each processor, they tarball or pull that all together, and then they compress it. It's a proprietary format. We just refer to it as XV4. But as we discovered, it's really just a glorified zip archive, which is not too surprising because why roll your own archive and compression algorithm when people have been doing this for decades and they're tried and true methods. So fortunately, we were able to figure out how to unpack this, and now we have a firmware image for each processor on the board. I included a link here to a nice public GitHub repo that actually provides some tools to help with this. So then, like I said, we only have 48 hours to do this. So we said, okay, let's pick the tiniest thing and see, can we get a viable exploit out of this? So this module called M1701, which at the time we had no clue what it was, but it was the tiniest in terms of number of bytes. So we said, okay, how do we do program analysis on this? Which then brought us to our next challenge, which is that unlike a traditional IT program, which usually has some kind of what we call program header that tells you some metadata about this program, like how to start it, what architecture it runs on, these firmware modules are completely stripped. You just have a blob of code and data with no metadata telling you anything about it. We don't know what the processor's architecture is. We don't know where the entry point, where the execution starts. We don't even know how to load it into a memory space. So at this point, we resorted to looking back at the hardware. So from some of the information online, we knew that this module goes onto this board. And by staring really hard at the high resolution photo, we were able to identify that this board actually has two processors on it, which I've squared in red. A Cortex M0, which is a typical tiny microcontroller, and then an M4, which is kind of the big brother version of the M0. And as it turns out, someone had already done a hardware teardown and had started to crudely construct a function diagram of how the components fit together. So that's how we were able to identify that the M0 in the blue box is connected to a microphone and a speaker. So think about, what could you be doing with a microphone and speaker? And then the M4 is connected to an accelerometer and a camera that's pointed straight down. By the end of this talk, we'll get into what this actually is. But for now, notice that the two processors are also connected to each other. They're also connected to a shared clock in the green there. So they are essentially time synchronized to each other. And then they have this ribbon cable that connects them to the electronic control system. So, okay, it's using something with sound. It's using something with visual and accelerometer, and it's passing that to the thing that controls the motors. You can probably start to get a guess of what this might be. But anyway, from reading the serial numbers, okay, we know this is a 32-bit ARM system. We still don't know what the entry point is. And we also don't know how to load it. But when we looked at it, it didn't look like it had a kernel. It looked like a fairly simple kind of bare metal program. So we basically YOLO'd it. We just dropped the whole thing into a virtual address space that's fairly typical for loading a program. And we ran our program analysis techniques to see, do we get control flow? Do we get data flow? Do we get something that resembles the structure of a legitimate program? And don't worry about this giant diagram. But basically, this is the call graph. So we attempted to identify where is the code in this blob, where are the functions within that code, and then try to find the calls and returns between those functions. And what we got was, something fairly reasonable. Like we are seeing things that look like functions, and those functions are actually calling each other. So we actually were able to fairly successfully recover some notion of the program's syntax. We have no ground truth, so I can't verify that this is the 100% correct call graph, but at least looks roughly connected enough that this is a pretty good shot. So then the question is, okay, we know a little bit about this program structure, but what is it actually doing? What is its semantics? So this is where we had to apply a lot of human level problem solving and basically say, okay, if it's a speaker and it's a microphone and it's ultimately connected to the motors, it's probably some kind of sonar system. And as it turns out, we did eventually verify that this is what DJI calls a visual positioning system. It's used during takeoff and landing when you're too close to the ground for GPS to give you accurate navigation. So it uses a combination of sonar, camera, and accelerometer in order to ensure a smooth and stable takeoff and landing. But anyway, getting back to our exploration, basically, we quickly understand, okay, the peripherals are what's going to tell us a lot about what's going on here. So the next thing we did was we went into a dive of trying to figure out what does this code communicate with. So we looked at the manual for ARM. It turns out that if you want to interact with a peripheral, you do that through something called memory mapped.io. And what you basically do is you map the registers of the peripheral device into a fixed memory region that's reserved. And this memory region is fairly consistent across processors. In the case of any ARM processor, it's in this region highlighted in yellow. So then we wanted to ask ourselves, okay, now that we know that the peripherals, if they exist, are in this memory region, can we identify any functions that touch that address space? And as it turns out, using a technique called a binary symbolic execution, which I don't have time to go into here, we are actually able to recover what this firmware to some degree reads and writes in and out of memory. And we were actually able to successfully identify the functions touching that region and which region they're touching. And then from the documentation from the system manufacturer, the company that takes that processor and integrates it into a working board, we could actually identify the functions for controlling what was labeled as two UART interfaces. So these are communication buses, and then one timer interface. So this is for controlling a clock signal. And as it turns out, if we go back to the board and we start looking at these pins more carefully, we actually found that there are 3 sets of service pins on here labeled U2, U4, and U6. And now we can take an educated guess that, okay, these are probably UART interfaces for communication. We weren't able to verify this, but presumably one of these connects the M0 to the sonar, one connects the M0 to the M4, and then one perhaps connects the M4 to the camera, the accelerometer, and then that upstream link to the electron control system. So quick little recap. I know I got a little bit into the weeds there, but basically what we were able to do is, given some knowledge about the hardware components based on the pictures, given some automated program analysis techniques of the code and data, we were able to identify the interfaces between these peripherals and get some idea that what we were dealing with here was a visual positioning system. So, okay, great. This took us the majority of our 48-hour budget. So now the question is, can we find any kind of exploit with this information? So naturally, if you want to attack a sonar system, the most obvious kind of attack that you do is you engage in either jamming, spoofing, or cancellation. You try to make the device incapable of getting a correct sonar reading, and thus, in this case, be unable to figure out exactly how far away from the ground it is. As you can imagine, during takeoff or landing, that is likely to result in a crash. However, if you want to attack a sonar system, what you need to know is what is the frequency of the sonar ping. If you don't know the frequency, you can't generate the correct acoustic signal to cause either a false reading or to cancel out another reading. So we figured out from analyzing the firmware that's using a peripheral for what's called pulse width modulation. And conveniently, the manufacturer actually gives in the documentation a formula for how to calculate what frequency the firmware is using based on the configuration in a collection of control registers. So once again, using some automated program analysis techniques, we were actually able to figure out what the firmware writes into each of these control registers, recover each of these variables, plug it into the formula, and get our frequency. The only gotcha that we ran into was when we read the control registers. As I alluded to previously, it was getting the clock signal from an external source, namely this external clock. Unfortunately, from the photos, we were able to get the serial number, look up what this quartz crystal is, and identify that it's a 12 megahertz quartz crystal. So plug that all into the formula. The number we got out was 40,000 kilohertz, or sorry, 40 kilohertz. And as it turned out, 40 kilohertz is a commonly used frequency for acoustic sonar systems. Didn't know it at the time, but that gave us pretty good confidence that we did this correctly. So finally, okay, we know the frequency, we can attempt to mess with the sonar system. It turns out we didn't actually have to do the attack in real life to verify that it would work. And that's because some researchers over in Israel already did the experiments. But what was interesting was that they did the experiments on a DJI Mavic Pro, whereas what we just analyzed was a Phantom 3. So we asked ourselves the question, do we really have to set up the whole real world experiment to verify that this would also, the attack they described would also crash a Phantom 3? Or can we somehow take a shortcut and know that the attack would work without actually trying it? So we looked at a photo of the board for the drone that they attacked, and lo and behold, we actually discovered, and this makes a lot of sense for a hardware manufacturer, they did not reinvent the takeoff and landing system, for each drone. This in the red box here is actually a copy and paste of the exact same hardware, and as we later discovered, firmware for the same visual positioning system. So whereas in the Phantom 3, which is a bigger drone, they made the VPS a standalone board. In the Mavic, which is smaller, they just took the exact same hardware layout and literally pasted it into the bottom left corner of this board. So all the same hardware, all the same code. It should come as no surprise that if we were to do this attack, it would work exactly the same. So that was our 48-hour sprint. We did go on to get the fire grant. So our case study here did give us the motivation we needed, and we were successful at that. But it raises a lot of questions of, what could be done to optimize this process. I'm running short on time, so I won't go into too much detail of all the projects my lab is working on. One of them is actually a poster in the back of the room, and I'm happy to talk about offline, the stuff that we're doing to figure out how do we go from half a board in 2 days to an entire system in, let's say, a week. So with that, I'm happy to take questions, and thank you for your time.
Quick question. So this is a described and demonstrated attack. Is there like a CVE or CWE for that sort of thing?
So the short answer is no. And that's also an interesting question because we have very robust infrastructure for reporting IT vulnerabilities. So like CVEs. CVEs do not map well into cyber physical systems. And part of that is because CVEs are assigned based on what are called CWEs, like categories of weakness, and those are all written from an IT perspective. So there isn't really a category for spoofable sonar sensor. So the short answer is no. I wouldn't be surprised if the manufacturer argues to some degree that this isn't a vulnerability because it's just kind of the physics of how a sonar sensor works. So yeah, there's actually a lot more work to be done in defining what are the categories of weaknesses for a cyber physical system and establishing something equivalent to CVE for physical systems.
So now that you've had time to analyze it or think about this system more, what greater exploit and bigger control? I mean, of course, if a drone is coming to kill me, it's already in the air. I don't care about its landing later. So now that you have, so how would you analyze the system with greater?
Right. So what our lab is working on is how to automate this process so that we can get from half a board in 2 days to the entire system in, let's say, a week. So as we start to be able to model the relationship between the peripherals and then the relationship between the different processors, we can start to get a larger model of the system. And that will then allow us to find more interesting exploits, exploits that are less likely to be known because people right now struggle with how to reason about the security of distributed systems and this whole notion that components that are secure individually composed together give rise to a vulnerability. So the short answer is I don't have a great solution yet for how to knock any drone out of the sky. But that's where we're trying to head over the course of this program. This program kicked off like a month ago, so we're still pretty early in the research.
Quick question. Do you encounter any code obfuscation?
Yeah. So it is possible for the hardware to employ some obfuscation. So for example, attempting to encrypt the firmware as it's stored on the device. This case study provided an interesting kind of side channel, if you will, which is that even if in this case, let's say the hardware is encrypting the image, well, we're able to go to the manufacturer's website and pull a unencrypted version. As you can imagine, if the manufacturer is more concerned about this, there are ways that they can make this harder. And that is one of the challenges as well with rehosting is how do you even get that code and data in the first place, presuming that the hardware might, for example, be encrypted.
Do you have any interest in going deep into the software stack at the component levels of the software versus the hardware, et cetera, et cetera?
Yeah. So those are both interconnected. So one of the things we're learning as we get into cyber physical systems is if you want to find usable exploits, you can't think of the cyber in isolation, and you also can't think of the physical in isolation. So a key part here is how do you draw that connection? So for example, one of the projects that we have is how can we automate the process of identifying what those peripherals are based on the firmware. So automatically recognizing from lots of open source examples, this is a particular communication protocol the firmware is using. These are the payloads it's sending and receiving. And thus, I believe this is a voter that's trying to talk to. Yeah.
And what about even going deeper in the sense of like the behaviors of the software that would be controlled as an algorithm or like sensor processing algorithms, et cetera, et cetera.
Yep. No, yeah. So the more we can leverage open source intelligence to recognize common patterns and be able to say, hey, I've seen a function that looks like this before. I think I know what kind of algorithm this is. This all goes towards how robust the model can get.
Questions? If no, let's conclude our first session. Let's thank Carter and Kamal. We're going to have 25 minutes coffee break.
This.
Yeah. Because I left them outside the door, and then I was like, somebody you know what?
All right.
Yeah.
Thank you.
All right.
Max, how are you doing? I uploaded yesterday. So I'm sure it should be there. Yeah. Because otherwise I don't have access to it. I don't even have my computer.
Okay.
I hope that's when more of a, conversation starts with the like, hey, how are you? Yeah. How are you doing? Okay, like after 2 years. I know. Zoom kills everything. I know.
Yeah.
So you have to say.
Yeah.
Also. From over there because I started
It's a little more like, it's not scary. Yeah. Great. And then I'm out in the office, I'm out the next 2 days. I also on Monday, I sort of wondered, Monday things I'm traveling to Western Ohio. But I don't think. We'll see. I should be able to. Okay. Okay. Thanks, Nicole. Oh, did you still this way? Yes.
Okay, recording is on in progress apparently. Thank you very much for being here today. I would like to give a brief preview of some of the things that I have identified as potential issues that we may have to address in 6G plus networks based on some of the technologies that are inherent and and also envisioned as part of it of these new generation of networks. And I would like to keep this as a conversation starter, right? I'm not probably going to present in solutions, but I would like to point out some problems that may arise. And I'm a firm believer of these conferences and these meetings serving as venues for discussions than just presenting what you have done, right? You can, of course, present what you have done, but if it doesn't spark any further discussions, then it's basically all for nothing. You could as well just publish a paper in a journal and you will be done. So let me, first of all, learn how to use this. Nothing else. Yes. Okay, now, all right. Yes, now it works. All right, so 6G networks, 6G plus networks, you may have all heard about them. And they are based on the foundation of 5G systems. And we look at the technologies that are being used between 5G networks that are being currently deployed and all the other technologies that are envisioned for 6G plus network. They're not all that different, right? The basic difference comes from the fact that there is the operation of these new networks will involve machine learning and AI, will be a lot more intelligent, and they will provide unprecedented connection speeds, ubiquitous availability, and intelligence of the artificial. So those are the cornerstones of 6G plus networks. And people are really not looking so much into the technologies that are being involved in this formation. but how to utilize, right? So those are the big things. The main means of operation here is not saying, oh, this is the type of standard that we are going to use, or these are the modalities of connection, but it's a collection of communication technologies to cover various scales, from pico to megacells, from IoT to satellite coverage. Everything under the sun belongs here too for communication. And that creates actually more challenges than initially let us see, right? As usual, securing any communication system, securing communication and connectivity in 6G plus systems is again a primary concern. And hopefully I will be able to make some connections between some of the technologies that sort of rise to the top as known technologies that are not researched all that much, and some of the new things that we can glean into them, and then that may present some advantages and challenges in securing such things. So we all know that securing data is well understood and investigated to the most part. We know how to protect it. We know how to make sure that it is private and everything else. Information, on the other hand, needs to be treated differently in these areas. So you may say, well, we all know how to deal with that too, right? We can differentiate the data from information, and information, in various communication systems how to protect that. And why should we even look into this? And I'll tell you give you some examples why this may be necessary. And yeah, valid question. Don't we know enough about securing information? One could argue to say we do. Here we are going to discuss a new technology that is being included in 5G and also projected to be part of 6G plus networks, which is the millimeter wave communication technologies. I'll present some examples of novel information leakage scenarios, okay, and ask questions for further discussion. So that's my promise and nothing beyond. By the way, if you look at your latest versions of your cell phones, look at the specs. You will be able to see millimeter wave as part of this set of communication modalities that they present. Whether they are used or not is a different one. But they are there. So it's not pie in the sky, something to happen in the future. So let's talk about millimeter wave technologies, which is basically nowadays the focus of my research over the past 5 years or so. They are all operating in the 20 plus gigahertz band, right? So bandwidths that are available there are pretty large, right? Because you have more room to grow to the left and right of your center frequency, if you will, right? But the signal attenuation is extremely high. And to combat that, directional transmission is necessary to focus your energy towards your receiver. So for that, traditionally, you either use physical waveguides, basically horn antennas, or you can do electronic beam steering through either analog or digital beamforming, right? So those are the two options that we have. Right. And the number of antennas increase, or the angle that you're going to use for these horn antennas, they can be adjusted and they have different gains, but at the end of the day, they all do the same thing. You point your communication in a given direction. It is no longer omnidirectional. There is a big deviation from the past. And, basis of these have been around for decades. Their use now becomes. It has significant ramifications, some positive, some negative. Highly directional communication and narrow beams allow us to use the space and spectrum very effectively, right? If I communicate, for example, with someone directly, then all the other surrounding areas, ideally, would be available for different types of communication sessions, etc., right? But it requires a high coordination between TX and RX. Gone are the days of RTS, CTS data act, right? For those of you who are familiar with those, right? A simple handshake is no longer sufficient. I need to physically find which direction I should point my beam to. That's a big burden, especially if you have large number of antennas and therefore your resolution, angle resolutions. If you use a pencil beam of a couple of degrees, about 360 degrees divided by a couple of degrees is a lot, right? Especially if the same thing needs to happen at the other end. You have to look at all coordination. your signals no longer go through solid objects. I put an asterisk there for a reason. I'll come back to that. Okay. So you have to have almost, you're required to have point-to-point communication, line of sight, or you can use reflections because things that don't go through objects are reflected. The waves will be. You can utilize them too. So this is an advantage, but it's a costly advantage. So you have to pay for it. You have to account for all kinds of different things. So this is basically where we start. Now, another issue is that in addition to communication, the same millimeter wave signals can be used for sensing as traditionally known as radar, right? So I can actually use the same signal for communication and sensing at the same time. And in fact, this is what we have people, working on for a while. And our starting point was what you see here, the use of the millimeter wave bands allocated for vehicular communication between 76 and 81 gigahertz, really high frequency. And we asked ourselves, can we utilize this underutilized resource for communication as well? We have developed a number of different solutions. So for example, here you see, using our developed algorithms, I can detect different targets with high fidelity and communicate with others at the same time. So I can form beams towards the communication pairs while sensing them. Right? So these are all possibilities that are not only theoretically possible, but also we have been able to show them their operational viability in testing. Now, here is this example of this reflection that I was talking about. You can communicate directly, or if it's obstructed, you can also communicate through a reflection. And the difference between this scenario and this scenario is that here I have a stationary part, which is our base station, and then I have a mobile receiver. So this is basically how it's going. Now, so some interesting insights. While we're playing around with these technologies and our testbed, we have found out that we can communicate and sense through some commonly used solid construction methods. Traditionally, we thought that it would be impossible to do so. Lo and behold, when we tried it out, it was possible. So what did we try out? First of all, we had this joint communication and sensing infrastructure that we have built. Okay, so we dub it JRC. This is a fully digital beamforming front end attached to our USRPs. It's actually a very simple system with 4 transmit and 2 receive chains. It's not all that capable, but it can show a lot of things. We have a blockage between a transmitter and an object, and this object can be sometimes also replaced by a receiver. So we wanted to see what's going on. We looked at several different types of material: drywall, again, everywhere; plywood, again, one of the most commonly used construction materials here in the US, as well as hardboard. So this is basically increasing in density, if you will, right? So in fact, it turns out that hardboard is the hardest thing to penetrate with millimeter wave signals, and our testbed is at 24 gigahertz, and drywall is the easiest to go. But the results are pretty much gradations of this. So sensing results, well, what we did was, here's a transmitter, here's an object, the plywood in between 2 meters. This shows the angle resolution, and this shows the distance resolution, and we are just looking at the sensing. So what we see over here is, well, this is the reflection of the obstruction here, right ahead of us, right? But then you see also there is some artifact here. There is some artifact here, right? And this is basically a metal, object that is in the back of the room, where we store a lot of our equipment. And this is the graduate student that stood behind that obstruction. So when we processed it a little bit further, we just did a very simple processing. What it was we looked at the frequency of reflections. How many of those points did we estimate reflecting back the signal? So, and by the way, this means that the signal originates from here, goes through this object, comes back, goes through this object again, and is received. So it goes through it twice. So when you do this analysis, you immediately see here the the metal object in the background, and the human standing behind the obstruction. So that's very good. And you can even see that there's significant differences between among different samples that you take. Like you can clearly identify it as an object there. Same thing, replace the grad student with a horn antenna and a receiver. Here's what happens. There is no blockage here. And here are the different types of materials that we use and the distance between the receiver and the blocker. This is nothing to sneeze at. The gains are all relative, but 30 dB is nothing to sneeze at. So this means that we can effectively transmit our data to this receiver, and it is being in fact received. At the same time, if this were to be held by someone, you could also detect that person here at this. So the traditional wisdom is, if I can somehow utilize the radar signals to figure out where you are, then I can also communicate. This says, well, even if you are behind, for example, a plywood or a drywall obstruction, I can detect you and communicate. It's a big deviation from the conventional, which actually creates a lot of different issues. Why? Because again, traditional people say, if you can't see through it, you can't communicate with it in millimeter wave. So people are using cameras, out of band sensing systems. This also shows that those approaches do not always work. I don't mean to say that I can peek behind every single obstruction, but I can see behind many of them. So this is basically a summary of what I have said before. So out of band sensing is not completely effective, and this both represents challenges and opportunities. And let's talk about information security inside systems. So let's talk about millimeter wave based communication systems and user information. Since we have high directionality here, if somebody wants to detect where I am, if I'm just using very narrow beams, then the probability of someone detecting where I'm located is very small with respect to an omnidirectional transmission. Omnidirectional transmission, you listen in, you estimate the signal strength. If you have an estimate of the propagation environment and the original signal strength, you can estimate the range. Here, you may not even hear that I am around, although I am very active in communication. But in the off chance that you do, you know exactly where I am located directionally. Right? This is a low probability event with fibers. I can reveal my information. Or if I go through it, and I will talk about that, through some sequence of sweeping the environment, I can reveal my location pretty easily. I can utilize the characteristics of the communication to characterize my device, for example, beam width. I can reveal that. The number of antenna elements are pretty much directly, extrapolated out of that. And the spatial temporal response to mobility. This changes to user too. As the user moves, so does the beams that follow them, right? If you can put a lock onto the beam, you can actually trace the beam to the location of the user as it moves. And the more data, different samples you have, the higher your resolution in detecting their presence. If not that, then wherever it's coming from. Right? So there are a lot of vulnerabilities that can be defined through the user detection and information about users' location, its devices, its device properties, etc. So there are protocol level determinism and vulnerabilities that we need to talk about. So as I mentioned, this is well beyond the three-way handshake. In order to establish the communication, a sequence of directional broadcast receive operations for link establishment need to take place. For example, the standards tell that somebody broadcasts omnidirectionally, the other end simply sweep to figure out where they receive it. Usually not very effective, but it happens. More effective way of finding the good paths is by sweeping at both ends, one of them going at a slower pace and the other one a lot faster. And this is done bidirectionally. So you actually start transmitting in all directions, although it's not omnidirectional all the time, you sweep all directions sequentially. So you can use additional sensor modalities for link maintenance, but it doesn't change the fact that you have to actually at some point start testing the The moment you start doing that is the moment you start giving an opportunity for an adversary to figure out where you are, or at least the direction with respect to where they stand. We end up using deterministic protocols. For most operations, including link discovery, transmitter receiver establishment, mobility management, you have very well established rules. Those rules are there so that you can, in fact, start the conversation, start the session. The moment you have a rule, it is right for this exploitation, characterization, operation disruption, and degradation. For some of the, like, let me give you an example of what might happen. If I were to, for example, reveal my presence in the network by an omnidirectional transmission, the clever way to go about that is not to jam my communication, in which case I would detect it, but it would be to inject just enough noise to disrupt my handshakes. For example, RTS, CTS, data is sent, and if my acknowledgement, which is a short packet, can be timed well, and if that pattern is revealed, somebody can inject a little bit of noise in there and disrupt my acknowledgement, the whole thing will start, right? Effectively, my performance is degraded so much that this link may be considered to be unavailable. Right? I don't need to be jammed. I just need to be disrupted. This is even worse in the case of these highly fragile millimeter wave systems too, right? So one of the questions that I would like to ask is, can we live without deterministic procedures? Can we randomize? And if so, how? What is the role of machine learning algorithms in obfuscating rule sets without sacrificing good performance? For example, there are, in fact, sensing methods rooted in signal processing, where you can apply sparse sensing procedures to randomly pull different directions to figure out where the signal source is, but they are usually not as effective as the deterministic. So what is the best way to do that? In machine learning, if we do that, can we improve the performance and go well beyond, the conventional wisdom of you have to train something here to apply it in the same location? Can that information be transferred elsewhere? Effective, of course, we can transfer it, but then how long will it take for you to train it? So, technology-specific compound attacks is what I'm calling this. Let's consider complex attack scenarios which utilize a series of technology-specific weaknesses, and all of which would have individual low impact, but they may have a high impact through coordination. So, for example, consider a millimeter wave transmitter receiver pair. You detect an active link, okay, on the line of sight path. Then you degrade the performance and force the communication to a reflected. For example, you just inject just enough noise at the receiver, so it becomes, the link appears to be unavailable. Then, assuming that this link is no longer available, the system would be forced to look for an alternative. If, for example, that alternative path is that wall over here, and I can place an eavesdropper behind it, then I can force the communication to go through that, beyond which I can actually easily record the communication and, mount my effect. What can be gleaned out of that is another question. But it presents an opportunity, an open door for that. I am well obfuscated from plain view. I cannot be seen, but I can effectively launch and compound attack to do that. And the question is, are we destined to play catch up forever? Right? So I have described an attack scenario, but is it really the end of the road? Right? So let's say I come up with a solution to this. If the attacker would, modify this and come up with something more clever, because believe me, there are people out there that are a lot more clever than I am, right? They can come up with a solution for their purposes. This is especially, problematic if we have different communication modalities, which is part of the 6G plus system. So one size will definitely not fit. But we have to look at the core issues and potentially find solutions to those core common modules so that we can, in fact, go through this information security issue and address potential attacks in pulse. And then there is also technology-specific anomaly detection issues. And this is basically a question that can be paraphrased as, can we differentiate between environmental factors and artificially introduced changes? What is the role of machine learning algorithms? Can they be transferable? If I train it here, would it work, let's say, 200 meters from here out in the open? Or if I train it here in this room, would it work in the next room over? So those are interesting questions to which I have honestly no answer. Okay. What is the role of experimental evaluation? You can sit down and do all kinds of theoretical work, or you can just do experimental work and collect data. There must be a confluence of those two approaches that will reveal some more information. But what is the extent to which we should rely on experimental evaluation? Again, their representative nature is challenged because the environment is no longer homogeneous. How adaptive are our solutions to deviations in attack mode? If we come up with a response to an attack, how quickly would the attacker change their behavior? What if they also use machine learning algorithms to counter them, right? To find the best modality to switch to. It's an interesting realm because they can not only switch the attack for on that particular link, they can also switch to different communication modalities, knowing full well that you have the capability of switching from millimeter wave to sub-6G to even good. And this may apply to all kinds of other systems. So again, I promised that I would ask a lot of questions and provide absolutely no answer. And I hope that I have kept my promise up to this point, right? So I hope that this part, if nothing else, just one or two questions in your mind, some interesting features that you may look into a little bit more. And if so, I will consider myself a successful presenter here. Thank you very much for your attention, and we'll be happy to continue the discussion. Yes, sir.
Range, 20 gigahertz.
Mhm.
How many meters are we talking?
Very good, very practical question. Well, my answer is going to be, equally engineering. It depends, right? So there are some experimental platforms that have really high gains where these links can be established over hundreds and hundreds of meters. In fact, Telefar, I believe, was capable of communicating over kilometer and a half.
In the 20 to 30 gigahertz range, or
Yep.
That's actually pretty.
Yeah, but
These giant.
no. The transmitters are about across.
Okay.
Like the front end, the antenna elements of the antenna array,
Right.
is about 20 centimeters in diameter. It's pretty small actually. But these are not mobile platforms. These are mounted.
So in theory, in a cityscape, if you had multiple arrays pointed around, you'd have some amazing direction finding capabilities.
That is true. And in fact, most of these, again, imagine that these signals are actually not going through hard solid objects like brick, right?
Good point.
So what you would do is you would create yourself an urban canyon of type of thing, or if you're walking around here, it will be installed on different walls of buildings, and best it can do is to track you as you pass through, and the moment your movement is done, you would switch on. But you also need to be consider the following: you don't only have one modality of communication. If you're that mobile, this may not be the best fit for you. You may want to switch to sub-6G and then, if need, you can come back. When you're stationary and you have a high volume of data to transfer, you can switch on. So these are all.
So I'm interested, of course, in trying to understand 6G and 5G.
Mhm.
And you had commented that there's an important aspect of directionality
Mhm.
And then you sort of, I was a little blurred in my mind between commercial applications and niche applications in military situations. Can you sort of comment on how directionality relates to 6G commercially and or in niche applications?
Okay, so let's start with the following. There are all kinds of promises about achieving super high connection speeds. What is the best way to achieve it? One should always ask themselves that question. There are physical limitations to what you can achieve on a given band, right? So sub 6G, let's say you have 300 megahertz of band in a given, but it's rare, but you can have. That's your dedicated. Because 300 megahertz means that plus minus 150 megahertz around your center frequency. You go to 24 gigahertz, you can go all the way up to plus minus, let's say 500 gigahertz on either. You go higher, you can actually go beyond that, right? You go to 76 to 81 gigahertz, there's a 4 gigahertz block that you can use. Of course, you pay for the price. You pay price for that additional bandwidth, which is all kinds of technological issues that you have to overcome, propagation thing, issues that you have to overcome. So that's given, but there's a possibility, right? So, and as soon as you go into that realm, since attenuation is so bad, the best thing you can do is to create narrow directional. There is technically no other way to overcome that form. And this is the only reasonable thing that I can. So, whether you want to actually increase your communication speed, or you want to use almost directional wireless links because you want to hide your presence in a military application, for example, the solution is the same. Right? Yes, sir.
The sense application portion of it, for the sense, what's the resolution that you can get on that? And then how vulnerable is that to like motion? Other types of stuff?
Should I give you the same answer? Depends. Right. So the resolution is a function of several things. The bandwidth that you have, or which you do the sensing, the number of antenna elements that you use, which translates to the beam width. The higher the number of antenna elements, the narrower the beam, right? And therefore, the better your resolution. Same thing with, for example, the detection of the speed of the object, the location, the angle resolution, the distance resolution. They are all functions of those. So in our case, we have about 12 degree angle resolution, which is horrible because we are only 4 by 2 system. If you go for, let's say, 8 by 8, it can reduce to almost 1/10. 1 degree resolution is possible. Right? So that's how it scales, right? And of course, the wider your beam, the worse off you are in detection. But wider your beam, less time you have to switch over from one beam to the next to establish to maintain your communication if you want communication. So there's always a trade-off there. So again, my answer, short answer.
All right, so you have no more questions. Let's thank Ellen.
Thank you very much.
Next. When is going to talk about 5G security. How is my PhD student? He's going to defend in one way. So he has worked with me since 2018. For a lot of stuff, the past 2 or 3 years, he switched topics on 5G security. So yeah, all resources.
Yeah, thank you very much for the introduction and having me here to share our recent research on 5G security. So Professor actually just now presented a lot of interesting attacks and vulnerabilities in the physical layer. Now let's getting back to 5G. And now my team and I are mostly looking at a higher layer, basically the layer 3 of the 5G protocol about the authentication kind of stuff, and we will talk about the vulnerabilities and attacks, as well as the different opportunities and challenges we identified to develop security services on top of the 5G infrastructure. So this is a work called the Security Enhanced 5G Radio Access Network. And this is a joint work between OSU and SR International. So first of all, let's have a brief overview of the background of evolution of the cellular network. So dating back to the 1980s, we found the first generation of cellular network was introduced, which was mainly for analog voice communication with very low data rates. And then around the 1990s, we have the second generation or the 2G network, where it starts to support digital communication, and we can use short message service or SMS for text communication, which is still prevalent today for us to receive, for example, the authentication code. And around the 2000s, we have the 3G network. It starts to support, for example, mobile internet, and we can use it for also for video calls. And around the 2010s, I believe we are most of us are very familiar with the 4G, or also known as the LTE network, and which offers us with a very high-speed data that we can access the internet and everywhere. And as we move along to 5G, so what 5G brings to us is the ultra high speed of data, and it's of course many new applications and opportunities, such as the massive Internet of Things, extremely low latency applications such as AR and VRs, as well as new network features and functions such as network slicing. So about this talk is about is centering around security. So why do we care about the security and privacy of 5G, or more generally about the cellular network? So this is all because of the monopole cellular network standard. So in fact, the cellular network standard, not just about 5G, but also for the legacy 2G until the LTE standard, but there has been very many vulnerabilities that can be exploited by attackers to compromise the 5G network and other devices. But these vulnerabilities may still apply to 5G standard, but are also very likely to exist even in the future G network standards as well. So before explaining why 5G is insecure, let me use a diagram to illustrate how a 5G device can connect to a network and obtain an IP address so that it can have access to the internet. So in a 5G world, we usually call any devices with cellular capabilities, such as a smartphone, a tablet, or other IoT device, as the user equipment. And here we call it as the UE. And we also have the base stations, which is connecting the UE to the 5G network. And in the 5G context, this is also called a base station or a genome. And the network operators can also provide the backend service for the 5G network. And this is hosted at a cloud server, for example. And in the LTE context, it's called the EPC core, and in 5G, it's called 5GC. So before UE establishes a connection between the network and an IP address, there are some transparent procedures going on that are the users are completely unaware of it, but it's going through very quickly. So these are the control signals that are being transmitted between the UE and network. So these are typically broken down into different procedures. So very initially, the nearby base station will basically broadcast its presence, some of the parameters and information to the nearby devices. So the UE will perform a procedure called the cell selection, where the UE will select based on the parameter from a base station to camp on a specific nearby cell tower. So the UE then will initiate the lower layer physical random access procedures so that it can camp on the base station. And then the UE needs to establish a connection at a high level and going through a procedure called the RRC. So this is very similar to the TCP three-way handshake that the UE will exchange messages such as request and response messages with the base station so that it can establish a RRC connection. And after that, the base station will start to relay all the messages transmitted from the UE to the backend, which is the 5G. And this is the procedure called the NAS procedure, where it basically the UE will try to authenticate itself to the 5G network operators by using its SIM information. So after these NAS procedures, the UE will have an encryption and integrity protection key so that the UE's future communications, such as the user data exchange between the network, will be fully encrypted and protected. So in this procedure, what can go wrong? So essentially, before the UE can establish a security context with the network, which is through the authentication stage. So all the messages, initial messages before this procedure, which means they can be unencrypted and not integrity protected. And this actually exposes a huge attack surfaces for external attackers to exploit these control signals. For example, eavesdrop, spoof, or flood these messages to compromise the base station or Apache infrastructure. So over the past few years, the mobile security community has identified a number of important threat models to conducting practical cellular attacks. So here I'm just showing a few typical examples, such as adversary UEs, where the attackers can launch malicious user devices to transmit malicious signals to flood layer 3 messages to attack the base station or other devices. And since those messages can be unencrypted and unprotected, and there could be possibilities for man-in-the-middle attackers that sit between a legitimate UE and a legitimate base station, so that it can eavesdrop or manipulate the messages in between these two entities, so that it can achieve, for example, spoofing attacks. And more recently, it has been shown there could be advanced attackers, which is known as the signal injection attackers. They can use some radio devices to override the legitimate signals between the UE and the base station. So this can be essentially viewed as a kind of stealthy man-in-the-middle attack, where the attacker just needs to transmit very low signal power to override the signal within the legitimate channel. So for our investigation, the cost for launching such a practical cellular attack is not that high. So typically, the attacker usually needs a commercial software-defined radio device, such as a USB 210 or even a lower-end kind of SDR. And the attacker can also use some programmable devices. It can be even like a Raspberry Pi that costs like only a few tens $80 for attackers to purchase. And there are already many open source cellular software stacks, such as the OpenAir interface, that the attacker can basically build a UE device and launch a base station using this device. And the attacker can also insert malicious logic into the open source code project so that it can establish, for example, a malicious UE or malicious base station in order to attack the 5G infrastructure. So let's review a few attack scenarios where practical attacks may happen to compromise and bring severe security implications. So let's consider, like for example, like digitally base stations, where an evil SDR and attacker nearby can use it to launch a BTS resource depletion attack, which is essentially a distributed denial of service, so that it can compromise the base station, so that all the mission critical drones and other devices will be disconnected from the base station. Another typical attack scenario is location tracking, where similarly an evil SDR device launched by an attacker can also use image extraction attack or the Suki catcher attack, which is already well known in the public. And this attack will allow the evil SDR to eavesdrop or actively or passively eavesdrop the permanent identifier of the user, such as the IMSI that is bounded to your personal identity. So because of this reason, the user's location can be tracked by the user by the evil SDR around the city. So after reviewing, there are so many vulnerabilities and attacks. So one simple natural thought is that can we simply fix the cellular standard in order to eliminate all these attacks? So unfortunately, the answer is currently this is still very challenging due to different concerns and reasons. So first of all, the cellular network standard, including 5G or even 2G standard, they are extremely complicated. And there are also numerous concerns from the network operators' perspective, because they need to consider the backward compatibility, the performance, and the overhead that may affect the user experience. So, this talk aims to answer this question: how can we defend against these attacks without even touching the cellular network standard? So in the following, I would like to talk about our key insights into how we approach this problem. So actually what 5G brings to us is not just the conventional upgrade with respect to the network performance, such as your bandwidth and low latency, but 5G also brings a lot of new opportunities, including the functions and new features that does not exist in the previous standards. So what we would like to highlight in this talk is about the Open RAN or the ORAN architecture. So what ORAN brings to researchers and integrators, it allows them to build normal security services on top of the traditional infrastructure, that is not possible in the traditional 4G or even the earlier standards. So what exactly is ORAN? So ORAN is also known as the Open Radio Access Network or the Open RAN. And it represents a new software-defined open cellular network architecture. It was founded in 2018 by a group called the ORAN Alliance. And so far, Open RAN has been adopted by over 32 mobile network operators in the world. So the key differences between Open RAN and the traditional 5G traditional network lies in the architecture perspective. So as we described before, a typical cellular network consists of three different entities: the user equipments, the base stations, and the core network. So in a traditional cellular network, the base station is nothing but just a monolithic and closed infrastructure, and it's highly vendor proprietary. With Open RAN, it essentially breaks down the traditional base station infrastructure into different components that are interconnected with standard interfaces, such as the radio units, the distributed unit, and the central units. Another key innovation in Open RAN is that it also introduces the additional layer for the control plane. So this is inspired by the software-defined networking principle, where all the control logic, such as the network management and detection, they can be all integrated into a centralized component called the near real-time RAN intelligent controller, or the near real-time RIC. You can see here within the near real-time RIC, there are many applications which are known as the X apps that are installed within this near real-time RIC components. So this X app can be written by third party to perform different types of functionality for network management, such as monitoring your base stations and devices activities, doing anomaly detection, or doing traffic steering or other kind of controls. So you can essentially imagine that in the Open RAN world, there will be an app store that many front-party developers or the network operators, they can develop apps, just like the smartphone apps installed on your phone. So in the future, the network operators may also use these X apps or R apps developed by developers to install in their network for them to manage their infrastructure very easily. Another key innovation in Open RAN is the introduction of the non-real-time RIC, which is handling some tasks with latency larger than 1 second. So according to the Open RAN specification and many use cases, this enables a lot of opportunities for example, machine learning or deep learning solutions to deploy as such called the R applications or R apps on top of the non-real-time RIC to help manage their network as well. So in summary, there are a few key capabilities of Open RAN. The first is, of course, the disaggregation between the control plane and the data plane, as the Open RAN essentially abstract the control logic apart from the data plane, so that it can enable network operators to introduce modularized applications such as the X apps and R apps building on top of the network control plane to manage their network functions. And Open RAN also enables different vendors to participate in the RAN development, and also it provides open standardized interfaces to connect all these components together. But still, if you want to develop security on top of ORAN, there are still a lot of challenges needed to resolve. The first, we call it the visibility challenge, because essentially you cannot defend against what you cannot see. So this indicates this is because the telemetry from the existing ORAN service models, they are insufficient for security. And we will need more fine-grained information other than the existing kind of standardized models provided by the ORAN Alliance. And the second is the extensibility, because the cellular attacks is keep evolving, and there's a need for an extendable framework to dealing with not only the current, but also the evolving cellular attack services. And also the efficiency must be high, because it needs to be capable of processing data packets and produce alerts with relatively low latency, so that it can match the requirement of the new network as well. So in this talk, which is heavily based on our NTSS 24 paper, is about we are presenting a framework called 5G Spectre, which is the first ORAN compliant layer 3 cellular attack detection service. And MobiFlow uses a few key technologies to solve the challenges, such as it uses a novel telemetry stream called MobiFlow that collects fine-grained information, including the UE stage transitions and aggregated RAN statistics. And 5G Spectre also uses a security X app called Mobi Expert that serves as a plug-and-play intrusion detection service on top of the near real-time RIC And this features with a P-based programming framework that allows network operators to easily program detection rules and signatures on top of their 5G infrastructure. So this is the overview of the 5G spectrum design, and it's broken down into several components, such as the RAN data plane, which is realized through some standard software stacks, such as the OAI, and some commodity hardware, such as USRPs. And the 5G spectrum layer consists of something called the SecSM agents that will handles the XF registration and subscription management, as well as the permission reports. And also, it has an XF or Mobi expert that uses the P-based programming framework, which allows the network operator to perform the attack signature programming and real-time notification. So I won't go into the details about 5G spectrum. So if you are interested, you can refer to our paper and websites, which I will post it at the end of this presentation. So let's talk about some of the evaluation statistics about 5G spectrum. So in order to evaluate the effectiveness of 5G spectrum, we have replicated many existing cellular attacks at the layer 3, including 7 different types of attacks in the literature, and we also replicated different types of variants as shown in this table. And we found that 5G spectrum can be programmed to successfully detect all of these attacks without any false negatives. And we will use one of the examples to illustrate how exactly 5G spectrum works. So this is a BTS resource depletion attack where the attacker is flooding with layer 3 message patterns to attack a base station. So with 5G spectrum, the network operators can use the P-based IDS signature to integrate a attack detection rule against this BTS resource depletion. So when this attack traffic pattern happens in real time, 5G spectrum will be able to automatically capture this and then generate a real-time alert to telling the network operator this attack happening. So we also have instantiated a 5G network testbed, which is hosted at the computer science lab at SR International, where we use several commodity SDRs such as USRPs and such as some cell phones to have a real life attack demo to show how 5G spectrum is working around those cellular attacks. And here I would like to show a demo video that we pre-recorded that shows that is basically the live demo happening at the SR International.
Here's the simple nature.
An ORAN stack by instantiating a security-focused service model called the SecSM and an analysis algorithm hosted within the RAN Intelligent Controller, or RIC. The SecSM is used to create an entirely new E2 telemetry stream, which we've specifically designed to give our XApps visibility into all the security-relevant state transitions and RAN statistics that we need to detect attacks and other security-critical activity or anomaly. So, to illustrate, let's consider a mission-critical example of a 5G network. Using a relatively low-cost commodity SDR, an adversary who is simply in radio range of your base station can take down the network using various layer 3 5G protocol attacks, such as the BTS resource depletion attack. To illustrate the threat, we'll use a few Android phones that are streaming video live through a 5G network, and we'll use an EDIS B200 USRP to target the base station. We'll also use our modified ORAN stack with SecSM to produce a mobile flow stream, which will enable 5G Spectre to detect the attack as soon as it executes. For the demonstration, we'll use our SERAN mobile network attack testbed, running Euro OAI, ONF's SD-RAN, and 5G Spectre. Okay, here's a live Zoom room with 2 Android phones with cameras that are pointing at monitors showing different YouTube fish videos. The upper left window runs our attack console, which controls an SDR that will be used to perform a live RF BTS resource depletion attack against our testbed's base station. The attack effectively expels all active client mobile network sessions from our network, killing our Zoom sessions. But here, 5G Spectre analyzes mobile flow to track the attack's malicious session establishment flooding pattern, and then immediately generates an alert. And here's another 5G protocol exploit that could be quite useful if one wanted to surgically disconnect just one mission-critical 5G device without disabling the entire network or disturbing other devices. This time, we will use a TIMSI spoofing layer 3 exploit against a single client device, which causes the base station to continually drop the victim device's connection. The setup of this demonstration is just like the previous attack demo. But again, our goal is to target a single victim device while not disturbing the entire RAN or other peer devices. Okay, so here are the same two phones streaming fish vids on Zoom. From the attacker console, let's launch the TIMSI spoofing attack using our SDR against the phone session that is displayed in the bottom Zoom window. The layer 3 spoofed TIMSI arguments of the attacker are reported within the MobiFlow stream, and we can see the resulting threat alert, including the victim's TIMSI and the detected exploit method. But more broadly, in recent years, the mobile security community has continued to uncover a wide variety of exploits against the latest 4G and 5G mobile link and session establishment protocols. These vulnerabilities are deployed globally and affect nearly every cellular network. In fact, here's a table of the various attacks that we've been studying, along with current status of threat coverage provided by 5G Spectre. The exploits the 5G Spectre addresses can enable adversaries to disrupt, spoof, or flood layer 3 messages to compromise the security, availability, and privacy of 4G and 5G networks simply by being within signal range. By the way, there will also be a full paper presentation of the 5G Spectre project that will be presented at the next NDSS conference in early 2024. For more information about 5G Spectre, MobiFlow.
Yeah, sorry about the echoing issue here. Let's. Okay. So in this work, I have presented 5G Spectre as a first layer 3 detection service on top of O-RAN with the 5G technology. And here we would like to also share what our vision is on the with respect to 5G security and outlining the challenges as well as the unique opportunities brought by the Open RAN. So so in order to develop security services on top of Open RAN, so the first thing we need to address is the visibility problem. So as I demonstrated in this talk, the existing O-RAN service models, they are transmitting insufficient security-aware telemetry so that it cannot support fine-grained security analysis on top of the Open RAN. So those are insufficient for detecting the existing layer 3 exploits. If you want to do layer 3 attack detection or more fancy attacks beyond that, then you will need more fine-grained telemetry and visibility capability. And this can be doing by augmenting, for example, the standardized E2 interfaces from the RAN data. And the second thing is about the analytics. So actually, in this talk, I'm presenting just an example of using an expert-based system called 5G Spectre to detect layer 3 attacks. But there are many analytic tasks that can also be performed from the X apps on top of the neural network. So traditionally, there is also a very important problem of detecting rogue or fake base stations. And more generally, you can also use it to detect anomalies within your 5G network, doing threat prediction and risk modeling, and etc. And one of the very exciting opportunities brought by O-RAN is the introduction of the non-real-time rig that can allow it provides an infrastructure basically for network operators to integrate machine learning or deep learning services on top of infrastructure, so that the network operators can use AI for doing training or inference on top of it to handle different types of security tasks. And another important aspect is that so the introduction of the Open RAN control plane also brings a lot of new attack surface to the attackers. So there, such as you can imagine in the future there might be some malicious XApps and IApps and different types of O-RAN services that could be introduced by third party into the O-RAN control stack that may be able to compromise some of the user privacy or like interfering the whole infrastructure. So there is a need for you to for us to do prevention, such as introducing a zero trust framework for the O-RAN cloud native control plane. Since these services are all hosted at a cloud native environment, such as using Kubernetes and Dockers. They are just containerized microservices. And you will need to ensure these different services they are not performing any malicious actions by doing this kind of prevention and enforcement. And lastly, we are also promoting a concept called AI ops or AI operations. And by combining all of the things that I described before, so all this can be using to automate some of the operations within the open band. So for example, from a security perspective, we can develop AI-based solutions for network operators to automatically develop security countermeasures, such as in this talk, we are demonstrating Party Spectre, which is just doing the detection work. But how this detection alerts and mechanisms can be incorporated with certain security countermeasures, such as doing device blocking and quarantine. So those kind of mechanisms can be developed using AI ops concepts to help network operators to automatically mitigate this threat without any human intervention. So similarly, so there are also many opportunities to do fault recovery, dynamic network slicing management, predictive management, as well as developing self-organizing network using the AI ops concepts based on the ORAN infrastructure. So that concludes my talk. Thanks a lot for listening. So we do have our research published at a public website called 5gsec.com, featured in a project called the Security Enhanced Radio Access Network. And we also have our 5G Spectre paper available, and we also have our artifact and source code published on our GitHub, so that you can use that to build your own 5G network and also play with the ORAN stack, install 5G Spectre, doing attack verification, and you can also develop your own X apps on top of the infrastructure that we provided. And thank you all for listening, and I'm happy to take any questions.
Thank you for that very helpful talk. With the line of sight being more and more relevant, apparently, what about the possibility of leveraging things that you can see? So if a drone is coming up right into your view, have you thought about leveraging, physical views or expert knowledge, or, so if, if I see this drone going right into my signal, can I batten down the hatches somehow and benefit?
So you are combining some line of sight technology to detecting some kind of anomalies and attacks happening on the drone.
Yeah. So I mean, because the thing is, if the enemies are starting to be visible because they have to be visible, then suddenly it's a new type of mitigation possibility, right? So like if someone's coming up and they're about to block my signal and then they're going to spoof my signal, I should be able to see that.
That's an interesting aspect by combining some kind of like physical behavior on the devices. Yeah, that could be something possible. I think using the ORAN technology by combining this with. But here we are mostly using some sort of like analyzing the network traffic, but integrating physical behavior is also very interesting direction.
Are there any other questions? So you showed that you used a several $1,000 like software-defined radio thing. Did you try using any of like the cheap? There's a whole family of like $20 software-based ones, the RTL and other things. Experiment with those and see.
But we do aware of other low-cost solutions such as the one that you just now mentioned a few bucks. But those kind of devices, they usually just support passive eavesdropping. So if you want to do like for example active attack, then you need to actively engage with the traffic and sending out malicious signals, and those low-end devices won't help. But we also have tried another solution. We use like a really IF SDR, which costs us around $600. That can also be used for doing the attacks that we described in this work. But I know I'm aware of there are other options such as the Lime SDR that are also low cost ones that at least cost the attacker a few $100s to launch an attack like that.
I have a quick question. So you mentioned earlier the cellular network is vulnerable because of the standards as problem. And you also mentioned it's hard to fix.
Yeah.
You're doing two reasons you listed, other reasons like, because of law enforcement or somehow they, yeah, I just want to hear, already have knowledge of.
Yeah, law enforcement, I don't hear any specific opinion about law enforcement preventing those security people fixing the standard, because those security issues, they are actually well aware in the standard. But I think the most reason is that although some mitigation has been discussed in the standard, but I think the most concerning concerns comes from the network operator's perspective. Because there's always a balance between security and performance. So you want to, so actually fixing those vulnerabilities is not that difficult. Maybe you can use, for example, public crypto, which is a like decades-long technology that you can simply encrypt some of the initial traffics. But that introduces huge overhead and concerns, including with respect to the performance and also the user experience. That's something the network operators care about the most. So there's a huge gap between the CGPP standard, which makes the 5G standard, and also network operator, which is the practitioners and the implement. So that gap needs to be filled in order to, for example, let those standards be realized in the practice.
Your device detect usage according to the stingrays?
Stingrays, you mean those kind of base station kind of, yeah, yes, those are a very interesting aspect. So actually, there is a limitation. So not every attack, not every defense, it has its own limitation. So here we are doing network based detection, which is we are deploying a defense on top of network infrastructure. So the stingray attacks that you are mentioning is something like the base station, for example, work base station is transmitting high signals so that it can attract nearby users to connect with it. So that's a different type of attack. So that's happening at the downlink side of the network. So there's also a limitation that all these kind of network kind of defenses cannot really handle that. But there are also some other ways to detect these attacks, such as using the user measurement reports. So there is a research that talks about using a measurement report from the UE. So basically, the UE will keep constantly reporting the measurement reports to the base station. So using that report, you can possibly also build own kind of defenses to kind of detect if there's a presence of the work base station transmitting high based on the signal strength and the power. That's a possible way to indirectly detect this kind of stingray attack.
Plus latency with them. Yeah. Okay. Any more questions? No, let's thank her one more time. He had posted more questions. Please talk. Also, by the way, if students are interested in 5G, right? Our lab do have this base station phones. We have about 50 phones, so we'll play a lot of resources. Okay, so lunchtime and enjoy the posting. Congratulations.